We look now at a couple of examples of root-locus plotting to just help improve your familiarity with doing so. One of them is quite straightforward, and the other one is quite a bit more involved. So let's get right to it. So the first example has a typical unity feedback case. Reference input, actual output we have a proportional controller and we have a plant. The plant is s plus 1, s plus 2 divided by s times s plus 4. We want to plot the root locus of this as k increases from 0 to infinity. So the first thing that we do is we put the open loop poles and zeros on the root locus plot. So I have an open loop 0 at s equals minus 1, so I'll put that down here. An open loop 0 at s equals minus 2, I will put that there. And I have an open loop pole at s equals 0 and an open loop pole at s equals minus 4. And that's over here. The next thing I do is I use the real axis rule, which says that the root locus is on the real axis to the left of an odd number of things. So I move my cursor from the right to the left, and so far I'm to the left of 0 things, 0, 0, 0, 0, 0, 1. So I put my pen down, and it's still 1, 1, 1, 1, 1, 1, 1. Then after I get to the 0, I get to 2, which is even, and then I get to the other 0, it's 3, it's odd, and then everywhere else it's going to be 4. So I've drawn where the root locus exists on the real axis. And we know that the open loop poles have to terminate on open loop zeros, which we already see has happened. And there's really nothing more to do. We could look for other things like real axis crossings. We'd find out that it crossed the real axis, the imaginary axis at k equals 0 right there, which is not a shock. We would look for multiple points. We would find none. We look for departure angles. We would find that they're all, well, this departure angle is 180 degrees and this one is 0 degrees. We'd look at arrival angles. We'd find out that that one is 0 and that one's 180. We could do all those things, but we'd find that this, in fact, is the root locus. So that one's pretty straightforward. Next one is actually quite a bit more difficult. It doesn't look that much more difficult, but it is. This here is, again, a feedback configuration, but it's not a unity feedback configuration. So immediately we have to be very, very cautious because the rules that we developed apply to the unity feedback case. So we have to go all the way back to the definition and say the root locus plotting rules apply to things that look like 1 plus k times b of s over a of s equals 0. So we have to look at what is the closed loop transfer function of this thing to get a b of s over a of s. And hint, it's not s plus 2 over s minus 10. So let's find the closed loop transfer function. It's the open loop stuff, k times s plus 2 over s minus 10, divided by 1 plus the overall loop stuff, k times s plus 2 over s minus 10 times s plus 3 over s plus 1. To clean it up a little bit, we multiply the top and the bottom by that factor there. And when we do so, I have this s plus 1, s minus 10 exists, multiplies the 1, goes away in the denominator, and that's going to cancel the s minus 10 here, but it's going to add an s minus 1 term in the product in the numerator. So in any case, this is the closed loop transfer function, and this is the characteristic polynomial that we want to set equal to 0 to find the closed loop roots. So the poles of T of S exist at s plus 1 times s minus 10 times plus k times s plus 2, s plus 3 equals 0. We can rewrite that, and we get 1 plus k times s plus 2 times s plus 3 over s plus 1, s minus 10 equals 0. So the thing that we're considering g of s, or for the purpose of plotting a root locus is everything I've just highlighted in green. It's not s plus 2 over s minus 10. It's actually that multiplied by that the transfer function block that's in the feedback loop. We could do that more generally, as it turns out, and we could say, what happens if I call this guy G1 and I call that guy G2? In general, I would have T equals K times G1 over 1 plus K G1 G2. And I would say, oh, the denominator is 1 plus K G1 G2 equals 0. And so if I'm plotting the root locus of that, I want this G1 G2 to be my B of S over A of S. We call that the loop transfer function. That's the entire loop without closing it is what we end up putting here. So we put the loop transfer function into the root locus plotting rules, and we use that to find where the closed loop poles are. So in any case, we're working with this. That's what we want to find. Where do the poles go as K changes from 0 to infinity? Well, we can start by putting the open loop or the loop poles and zeros down. And we notice we have a 0 at s equals minus 2. We have a 0 at s equals minus 3. We have a pole at s equals minus 1. And we have a pole at s equals plus 10. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right there. That is our starting point. Next thing we do, we consider where does the root locus exist on the real axis. So we take our cursor and we go to the right of everything, and then we move left. When we cross an odd number of things, we put the pen down, and then it becomes even, and then odd, and then even again. So what I've just highlighted is where the root locus exists on the real axis. Then we think about how many asymptotes will there be. Well, there's going to be n minus m of them. Equals 2 poles minus 2 zeros equals 0. There's no asymptotes. I could think about departure angles, but really the real axis rule has already told me what those are. I can calculate this departure angle. It's 180 degrees, it turns out. I can calculate this departure angle. It's 0 degrees, as it turns out. I can calculate the arrival angles. The arrival angle to this guy is 180 coming from the left, and the arrival angle to this guy is going to be 0 degrees coming from the right. So far, that really hasn't helped make the root locus a little bit more clear. We know we're not done because the poles have to somehow end up at the zeros, and we don't have a path for them to do so yet. If that's going to be the case, at least one of the poles has to cross the imaginary axis, and maybe there's multiple crossings of the imaginary axis, as maybe this pole goes across and then they split and do something, or maybe this pole just really zooms over there and it crosses and then they split and do something. But in any case, at least one of the poles has to cross the imaginary axis if they're both going to terminate on the zeros on the left. So it's going to be pretty helpful to figure out what is the stability boundary. So we look at the closed loop characteristic equation. We look at it, which is setting the denominator equal to 0. Which version am I going to use? I'm going to use this guy here. S plus 1 times s minus 10 plus k times s plus 2, s plus 3 equals 0. That's the characteristic equation. This here is what we are going to use inside of a Routh test from the last chapter to figure out the stability boundary. So multiplying out the first factor, s times s is s squared. I've got 1s, I've got minus 10s gives me minus 9s overall, and then plus 1 times minus 10 gives me minus 10, multiplying that first term out. Multiplying the second gives me k, multiplying s squared, and the sum of 2s and 3s is 5s, and then the product of 2 and 3 is 6, so I've got k multiplying s squared plus 5s plus 6. Then collecting like terms, I've got 1s squared, and ks squared gives me k plus 1s squared. I've got minus 9s plus 5ks, 5k minus 9s. I've got minus 10 plus 6k, 6k minus 10. So everything's grouped. It's ready for putting into a Routh array. So I look at this polynomial. Highest power of s is s squared. So I start my Routh array by writing s squared. And then I know I'm going to have an S1 and S0 column, rows, so I put those in. Then I put the coefficients from the polynomial into the Routh array. So the k plus 1 goes there, the 5k minus 9 goes there, the 6k minus 10 goes there. So I filled in the top two rows, and I can put zeros, as we remember, everywhere else. That leaves the this term here, which we will call B1. So B1 equals minus 1 over this guy here. I'm going to call it A2. A2 times the determinant of k plus 1, A2, 6k minus 10, and 0. And the determinant is going to be equal to 6k minus 10 times A2, and all of that is over A2. The A2's cancel, and I get, that's minus 6k minus 10, so it's plus. So I get 6k minus 10 showing up in that B1 term. Now we need to figure out what is the condition for stability. So for stability, the left column has to either be all positive or all negative. Look at the same criteria no matter which way I choose. So I'll just say let them all be positive. So that means that k plus 1 is bigger than 0, or k is bigger than minus 1. That's the condition required for stability imposed by that first term. Then I've got 5k minus 9 is bigger than 0, which gives me 5k is bigger than 9, or k is bigger than 9 over 5. That is the condition for stability imposed by the second row. Finally, 6k minus 10 is bigger than 0, 6k minus 10 bigger than 0, 6k is bigger than 10, k is bigger than 10 over 6, and that's, or k is bigger than 5/3, same thing. That's the condition imposed by the third line. Now remember, all three of these must be true simultaneously, so I find it helpful to do a number line. First criterion says k must be bigger than minus 1. The second criteria says k must be bigger than 9/5. Third criteria says k must be bigger than 10/6 or 5/3, which is like this. For all of them to be simultaneously true, k must be bigger than 9/5, which is 1.8. So that is our stability criteria. When k is equal to 1.8, I have a situation where I've got marginal stability. If it's bigger than 1.8, completely stable, all the poles are in the left half plane, but less than 1.8, it's not actually stable. So this gives me the value of k for marginal stability. Notice that when k equals 1.8, this here is 0, and in fact that entire row is 0. And we remember from the Routh test that when an entire row is 0, the row immediately above it is a factor of the equation, the actual transfer function, the denominator of the transfer function, the characteristic equation, rather. So that tells us how to solve for the point of crossing the imaginary axis. I know it crosses the imaginary axis at k equals 1.8, but where does it cross? This is where the Routh test case number 3 is really helpful. So what we're going to do is we're going to say when this row is 0, the previous row is a factor of the equation. So I've got k plus 1s squared plus 6k minus 10 would be the A1 row I would figure out. So k plus 1 all times s squared plus 6k minus 10 times s to the 0 equals 0 is a factor when k equals 1.8. Let's put in k equals 1.8. So that's 9/5 plus 1 is here. And then 6 times 9/5 minus 10 is there. That equation is a factor of the roots of the system. And plugging that in, what am I going to do? I'm going to multiply both sides by 5. That would be easier. So I would get 9 plus 5 s squared plus 6 times 9 is 54 minus 50 equals 0. So I've got 14s squared plus 4 equals 0, or s squared equals minus 4 over 14 equals minus 2 over 7. So s is plus minus j times root 2 over 7. That's where the locus crosses the imaginary axis. So this is helpful. I had a 0 there, a pole there, and a pole there. Now I know I've got imaginary axis crossings, somewhere like there. Incidentally, the other rows of the Routh test are interesting. This k equals 1.6. You can imagine if I have two crossings of the imaginary axis, what had to happen was this pole had to cross first. This pole had to meet it at some point. They had to break away and cross. And then they go across here. They go across here somehow. They join together, and my root locus is going to look something like that when I'm done. When k equals 1.8, I get to the point where all of the poles are now, or when k is just a tiny bit bigger than 1.8, all the poles are in the left half plane. This point here happened. I had a stable pole that crossed into the right half plane. That actually happened at k equals, what is the other number here? It's 1.66. 1.66. So this other row in the Routh array is actually meaningful. It's actually saying, well, there was an imaginary axis crossing at that point. It just isn't the crossing that gives us ultimate stability. I have to get to this point here when all of the poles cross to get ultimate stability. And that's kind of interesting. K is bigger than minus 1 is also interesting. If I were to put in negative values of k equals minus 1 is a place also where I would have an imaginary axis crossing, but we won't get into that until later. So we can now kind of sketch what this root locus looks like. To really finalize it, though, we'd like to know where is that breakaway point and where is that point there? Where do the branches of the locus intersect? And so we have to use the breakaway point rule. So k of s is minus 1 over g of s, we said. G of s, this is minus 1 over g of s. And I can multiply the terms out. That's going to make it maybe easier to do the actual derivative. But there we have it multiplied out. Doing the derivative of a quotient is always a little bit tedious, but we have the derivative of a quotient is the numerator times the derivative of the denominator. So there's the numerator, there's the derivative of the denominator. So notice I used that form for the numerator and that form to get the derivative of the denominator. And then minus the derivative of the numerator, which I used this form, times the denominator, which I used the other form, all divided by denominator squared. And we're going to set that equal to 0. And then there's some algebra multiplying these terms out, which again is a little bit tedious, but it's not too hard. We just go and we do it, and we find that we have this equation minus that equation equals 0, and we combine terms, and it turns out that the s cubed term conveniently goes away, and we end up with a quadratic equation that we have to solve in order to find where the breakaway points might be. Quadratic equation, this is the quadratic A, quadratic B, quadratic C. So I have minus B plus or minus B squared minus 4AC over 2A. Putting all the numbers in, I believe you will get that result. That is where the breakaway and the break-in points are, where the branches of the root locus intersect. Put that in your calculator, get a numeric answer. We have a point, a breakaway point at 0.118 and a break-in point at minus 2.4. So finally, we're at a position where we can complete the root locus pretty accurately. Open loop 0 at minus 3, at minus 2, open loop pole at minus 1, and at 10. We have a breakaway point at about 0.1, break-in point at about minus 2.4. We have imaginary axis crossings at, I think it was square root of 2 over 7 times j, somewhere around there. And the rest is just filling in the locus and something like that, and we're done. So that was a fairly comprehensive example. If you can work your way through that example by yourself, I think you're in pretty good shape for being able to plot root loci. And the next thing we're going to look at then is how do we use this as motivation for design. We'll actually have a whole chapter on root locus design, but we'll at least have a look at it in this chapter before concluding.